All right. So anybody want to take a stab at how you maybe approached it? What was your setup for part A? Or did anyone try it? If not, that's okay. I'm gonna take that as a no. All right. So we have a freshman here, at Dexter High School. She decided to use money from her part-time job at a public library to open a savings account with the intent of buying a car when she got to college. Okay, so the key here is she's a freshman, right, in high school, which means that by the time she gets to college, that's 4 years, right? At least that's the intention. All right. So what fixed amount of money or what fixed amount must Danielle save each month in order to purchase an $8,000 car in 4 years if the savings account interest is 4% compounded monthly? Okay, so there's quite a bit of information there. So let's go ahead and maybe break this down. All right, so she eventually wants to get to 8,000, right? So ideally, right, that's the final value that we intend on reaching. The account interest is 4% compounded monthly, right? So then if we had an N value, because it's monthly, then it's 12 months, right? N for 12 months because that's the compounded monthly. Interest rate, right? So we have R, because it's at 4%, then go ahead and shift that over, make that a decimal. So we're looking at 0.04 instead. And then there's a couple other things that we don't really have yet, right? Because they're asking us what fixed amount must she save each month, right? So if that's the question they're asking us, then that means we don't know, right, if this is the formula that we're trying to fill in as much as possible. Which one of these represented the amount for each month? Was it the A value or the I value? So typically I is your initial, right, which represents the initial deposit. But we don't know that either, okay, because she doesn't say whether she's going to start a savings account with a certain amount. So we don't know the initial. And what we are being asked to find is what is the A value, right? What is it that she plans on depositing each month so that she can get to the 8,000 after, a certain amount of time. Okay, so then let's go ahead and start filling in about as much information as we can into the formula to see where she ends up. Oh, cool, we got somebody else. Okay, so setting this up here, then what we're looking at is, oh, sorry, I got a helicopter flying in the background. All right, I'll wait till it passes. I'll be right back. All right, guys, sorry about that. Okay, so trying to fill in about as much as we can here, and so if we start with the formula given from before, let me just write it down right here real quick. F is equal to I times a 1 plus the rate to the, I'm sorry, 1 over R, 1 plus R over N now, because we're not compounding once per year, it's monthly, right? So we need that N value to be there to the N times T plus the A value times 1 plus R over N to the N times T minus 1 all over R over N, right? So that's kind of like the big formula now. And so let's see what we can plug in here. So for final value, you're looking at 8,000. Now, we don't know what you put in for the initial. In fact, it gives us no information about the initial amount. So what assumption can we make about how much money she will deposit initially? Right? The question we're trying to answer is what fixed amount does she need to save each month? So we're trying to solve for A, but if we're not giving any information about any initial deposits, what do you think we can plug in for I? Any ideas? So in this case, I think we're gonna have to make the assumption that because there was no initial deposit, we're just gonna put 0 for now, okay? Because the reason why it's important to identify if there is initial or not is because if there is an initial amount that is deposited, then we can then utilize that to start earning interest from the moment that the money goes into the account. So we have to then say that there is no initial amount, okay? She's just gonna automatically start making monthly deposits, okay? So for now, we're gonna leave this as 0, which then if you multiply it times whatever, right? 1 plus our rate, which would be 0.04 divided by 12. In this case, it's 12 to the T, right? In this case, we discussed that because she's a high school freshman, then by the time that she actually graduates, we should anticipate that that's only about 4 years, right? So then the time is 4. But once you calculate all of this and then you multiply times 0, this all goes away, right? It all becomes 0, right? So I filled it in, but really it's not going to affect the amount of interest or amount that that's going to increase by. All right. So now as we move on, okay, we're really only going to be dealing with the right part of the equation. So then we still have A because that's still the big unknown. And then we can fill in the rest. Okay, so we have 1 plus 0.04 all over 12 to the, in this case, the n is still 12. The time is 4 years, minus 1 all over. Then you have your rate divided by your compound factor one more time. Okay, so it's 0.04 all over 12. Okay, so can you guys see why then this part is now completely irrelevant? Because the initial amount of money, which was nothing, is not going to earn anything over time. So the only thing that we can calculate or that we can count on is those monthly deposits earning interest over those 4 years. Okay, so because we still have a variable to solve for, which is A, we have to clean up the rest. Okay, so I'm going to go ahead and bring everything down and then we can clean up after that. So we have 8,000 is equal to A times 1 plus 0.04 over 12. I'm going to go ahead and change that to the 48th power minus 1. And then again down here, 0.04 divided by 12. Okay, so I think our best bet right now is to clean up about as much as possible. We could go ahead and then divide. We can solve for A. Okay, so let me go ahead and let me share my whole screen so you can see my calculator this time. All right. Okay, so let's go ahead and start with the, I'm going to start with the denominator actually, just to see what that becomes. Hopefully it's something that's not ugly. Oh, yeah, it is ugly. Okay, never mind. All right, let's see. So we got inside of the big parentheses, the smaller parentheses there. Let's go ahead and clean that up. So we got 0.04 divided by 12. I'm going to start right here. 0.04 divided by 12. Okay. And then to that, I want to add 1. Then I take this value to the 48th power. Okay. And then we can go ahead and subtract 1 from this. All right. Okay. So then now we divide this. This is divided by, inside parentheses here, I have 0.04 divided by 12. And then that should equal 51.96. Okay, so we can go ahead and say that this is A. Oops. A times 5196 is equal to 8,000, right? So to solve for A, we can just go ahead and divide both sides by the 5196. And now let's see what we get. So 8,000. All right, cool. So here we're going to get that A, the recurring deposit amount, has to be just below $154. So 153.96. A is equal to 153.96, which is approximately $154, right? Okay, and so that's the setup. So the tricky thing about the question is that you're not giving any initial information. So then you would have had to plug in 0 there. And then that way you solve only for the recurring deposit every month. Okay. Are there any questions about that? We okay so far? All right. Yes, so okay, cool. So then it asks how much of the $8,000 is money that Danielle deposited and how much of it is interest, right? So how can you decide on a technological tool to help you complete the task? Okay, so then let's go ahead and utilize that tool that we looked at last time, right? Because we can do it algebraically. We have the tool though, so let's go ahead and use that because we know the rate, we know it's compounded monthly. And we're trying to get to this fixed amount. So maybe if we take a look at that, we can find it. So let me pull it up. Okay, so here, principal amount was nothing, right? She didn't invest anything at the beginning. She had an annual interest rate at 4%. The monthly contribution, in this case, let's go ahead and use the exact value. Hopefully it gives a little bit of a more precise calculation. Oh, sorry. So it was 153 with 96 cents. Oh. Oh, okay. I guess it doesn't let me put in the decimal. Let's go ahead and round it up. We'll just put 154. And the length of the investment was only, let me see if it lets me change this. Oh man, that's too bad. All right, never mind. Okay, it's not gonna work because it doesn't let me type in the 4 years. So we might have to do this. Might have to do this by hand. Okay, that's okay. So we did a problem like this last time where we had to look at how much was it that the investment was worth, and how much was contributed. Well, if we know that she's investing $153.96 every month, right, for 4 years, well, we know that then that represents. We can kind of break this off right here. $153.96 for 4 years. I'm sorry, 12 months out of a year, okay, for every month. And then again, times like the 4 years that she's going to do this. So basically, she's multiplying this amount, $153.96, times 48, okay? So that's her contribution. So we can take this value, multiply it by all right. So do you see how the amount that she's contributing doesn't completely get her to the 8,000 alone, right? It only gets her about $7,390. And that's because the other part of the money is then being generated through the interest, right? That's taking care of making up the difference. So here, 73.90 with 8 cents. Which means then that the remaining amount had to have been earned through interest. So then in order to find that, you can just subtract it from 8,000. Okay. So this is her contribution here. And then whatever we can get from this, it would be just the interest that was earned. So she earns a little over $600 in interest, $609.92. Right, so this is the interest earned. And that's pretty much it, right? So if they ever ask you, if you ever ask the question about how much your contributions are, well, you know that your contributions are based on what you're paying into the account monthly, right? That's always going to be your A value. The A value, this is not counting any interest. This is how much money that you yourself are putting into the account. If you want to find out how much you've done over the course of several years, obviously it depends that if you were making monthly contributions, that means you were making 12 contributions per year, right? So 12 payments of $153.96. And then you did that for 4 years. So overall, you made 48 payments into the account worth this amount. Okay, so overall, you're contributing to the majority of the savings. But then whatever difference is left over, right, that's what the interest earned would be. So it's just a quick multiplication and then a subtraction to find out each one of the two totals. You don't have to go through the entire process of like plugging something into this giant formula all over again, because if you just use a little bit of like logic, you can get there. Okay. All right. So then, yeah, so then part C was asking, how did you decide on a technological tool? Well, in this case, we didn't, right? Because it didn't work for us. We couldn't change it to 4 years, right? It was stuck at 5. All right. So that's pretty much the CYU there, just kind of getting you comfortable with utilizing this large formula, and then understanding that sometimes there are scenarios where you won't have an I value, and that's okay, right? If there is nothing to initially invest, and she's only worried about what amount of money she needs to invest monthly from the time she opens the account with nothing put in there to start, then it's still solvable. Okay. All right, guys. Are there any questions on that? Because that pretty much wraps up all of the investigation number 3. And I'm going to go ahead and move on to investigation 4 if there's no other questions. We're okay so far?
Yeah.
All right, cool. Cool. Okay, so now let's move on to something new finally. taking a look here at investigation number 4. So investigation 4, this is the last one of this lesson, right, which is this really long chapter. A lot of it is very similar to what we've been looking at, except that now we're introducing this new number. It's called the number E. I want you to think of the number E as like the number pi. Pi, right, is kind of like this abstract irrational number where you're familiar with the approximation, right? It's 3.14, and then it keeps going, 159, yada, 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 right? There's another number out there very similar to pi, which is used a lot in applications such as compound interest. So pi lives in the realm of like geometry, right? Because it has something to do with circles. So we don't really use pi in algebra very much. But E is like the equivalent of pi. It's like its cousin, but its applications are based more in algebra and exponential functions and logarithms, log, and things like that. Okay, so whenever you see E, I just want you to think, okay, it's like a number like pi. Okay, and so we're gonna do like an activity here that kind of shows us what E is approximately equal to. So I'm not gonna give it to you just yet, but I want you to know that E, okay, basically related, not related, but that's a bad idea because I don't want you to think of E related to pi. They're completely separate, but they're similar. It's similar to pi in the sense that it's this recurring decimal number that doesn't end, but it has huge applications to algebra and exponential functions. And that's essentially what compound interest is. It's an exponential function, okay? All right, so that's just like a quick overview. Interest. All right, so that's just a quick little aside there. All right, so let's go ahead and just kind of read the intro together. I'm gonna read it with you, so we kind of understand what's going on in these first few problems. Okay, so compound interest and the number E, right? There's a huge relationship there. So the reason why E is brought up is because what happens when you start to compound things at a much faster rate, right? So imagine that you compound an account just one time a year, right? That's annually. You can speed up the compound rate and you can compound it twice a year, semi-annually. You can speed that up even faster. You can do it 4 times a year. We call that quarterly. You can do it monthly, then that's 12 times a year. If you choose to do it weekly, then that's 52 times a year. If you choose to do it daily, then that's 365, or I think the banks use 360, so 360 times a year. But then what happens if you choose to have done it every hour, or every minute, or every second, right? What happens when you are continuously compounding something versus just compounding it 4 times a year? And that's why E is useful, because sometimes some banks, they utilize the number E to do continuous compounding, which means that it's compounding every single moment, right? At a certain percentage, very small, but it's doing it continuously, right? So the benefit of that is that if you have an account that is continuously compounding, it's to your benefit. But what if you owe a credit card that has interest and you owe money to that credit card and then your interest is being compounded continuously, right? Just imagine the potential for the amount of interest that could rack up either against you or for you, right? So that's where the importance of the number comes in, because it's very hard to determine how things are being compounded if it's continuously, because what does that mean, right? Like, what is continuous, right? It just means it doesn't stop, right? At every single moment, there is a small percentage, a very small percentage in which your interest was compounded, okay? So it's very hard to calculate. Therefore, that's why the number E is this number that's also kind of hard to even like conceptualize, right? Very much like pi, all right? Okay, so now here's the situation. In problem 1 of investigation 2, going way back, we can refer back to it in a second. Okay, it's basically saying that we calculated the value of 3 accounts with initial deposits. So we had a deposit of 1,500, and you were paying that was paying a 4% annual interest rate. And we checked it versus after 1 year, after 2 years, and after 5 years. Okay, we calculated it with 3 different types of compound rates. So one, it was compounded semi-annually, the other account was compounded quarterly, and then the third account was compounded monthly. Okay, so just to kind of refresh your memories, we have that here. Let me pull it up. And it said it was investigation 2, so let's go back. And this is the problem right here, right, that they're talking about. We had an initial deposit of 1,500 in a 5-year CD. The interest is paid at 4%. And then we did these calculations based on whether we were going to do this at a semi-annual rate, at a quarterly rate, or at a monthly rate. And then here's basically what we determined, right? We took each one of those. And if you look down this column, right, just at the first column, don't even worry about year 2 and year 5. But just after 1 year, I want you to notice something. That when we compounded semi-annually, right, 1560 with 60 cents. If you compounded it quarterly, this is the amount of money more that you would get by compounding quarterly, right? Doing it 4 times a year versus just once. And then there was another change in amount if you decided to do it monthly, right? It was about 20 cents more. So semi-annually, when you compound less, it earns you less interest. When you compound more, so if you compound it quarterly, it earns you more interest. But if you compound it monthly, it even gives you more interest, right? So imagine that there would have been like a plan 4, and plan 4 was weekly, right? You compound it 52 times a year. Imagine what that might be. And then what if you compounded it daily, 360 times in a year? What might that look like, right? We don't know the exact number, but the idea is that if we were to compound things on a weekly basis, you would have more money in the account, a few more cents, than if you would have compounded monthly. And if you would have done it daily, you would have gotten more interest than if you would have done it weekly, okay, and so on. So that's kind of the idea of what it's trying to get to, that the more frequently you compound something, the more interest you're earning. Whether it's small, doesn't quite matter, okay, but it's still earning you more. All right, so let's go back. Okay, so that's basically what he's saying, what they're saying here. You found that the account for which the interest was compounded more frequently, right, the one that's compounded more frequently, earned a better effective yield, which means you earn more interest on that. Okay? This process could be continued so that the interest is compounded every day, or every hour, or every minute, or even every second, right? And that's what continuous compounding does, okay? All right, so then the key questions here for us is to find out, well, what is the number E and how is it connected to frequent compounding of interest? All right, so we're gonna spend some time understanding where E comes from. And then can you predict the future value of an investment with a fixed APR that is compounded continuously? Okay, so then eventually this understanding E then allows us to then generate a new formula, and then we can use that formula if we ever encounter a situation that we're compounding continuously, all right? So the first thing here is, what is the number E? I'm gonna go ahead and kind of skip that first problem because it's a little bit vague, a little bit confusing. But here's what the E, where the number E comes from, okay? I'm gonna go ahead and move it to the next page. There's a formal definition of E, and it utilizes limits, and limits is something that kind of comes into play in calculus, but hopefully you'll follow me here, all right? So the number E, okay? The number E, here is the formal definition of E. E is the limit as n goes to infinity of 1 plus 1 over n to the n power, okay? And you're probably wondering, like, what the heck does that mean? Basically what it's saying here is that in order to reach E, you have to utilize a number large, like a large number. That's why the limit here is that saying that the closer you get to infinity, right? So imagine that you're able to substitute a number here for n. The closer you get to infinity, the larger the number, the closer you're going to get to the number e, okay? So we're basically, limits are approximation that get you about as close as you can possibly get to a number that you're looking for, all right? And so the idea of approaching a limit is what the book utilizes here, but they use it like in a table format, right? So they're giving us n values for us to plug in, right? Now the n value in this case does not represent the n value of a compounding, okay? I don't want you to think about it at like that so much anymore. But we're using n because that's just like the definition of the letter E, that we utilize these values that when they get larger, we're going to see that they're approaching a certain number. And then that number that we're approaching is going to give us the number E. Now, they're telling us down here that the value of E is approximately 2.71828. Okay, that's what we're trying to get to. Okay, but I kind of want to go through this process to see how it gets there. All right, so you'll see down here that the number to which the values in the table are converging is a special mathematical constant. Okay, and we label that letter E. All right, so let's just kind of play around with this table. Let me see if I can take a screenshot of it real quick, and then we'll work on it. So the larger the cat value, the closer we'll be to what the real number of B is like. Small, we're going to be far away. So he's kind of like there. Okay, so first, plugging in. So let's see what we got. So we have 1 plus 1 over 1, right? So I'll do it down here. 1 plus 1 over 1. And then again, n shows up there as the power, so then to the first power. So if you were to simplify the inside, that basically gives you 1 plus 1 to the first power, and that's just 2 to the first power, which is essentially just 2, okay? So take a look, right? The number E is approximately this, right? So in terms of our limit here, when n is small, the number here is 2. Okay, now it seems like it's pretty close to 2.7, but in terms of accuracy, that's pretty far away. Okay, so as n gets larger, the number here, the output should get closer to 2.718. Okay, the larger n gets, the closer we'll get. And that's what it means to converge on something, right? We're converging to a certain point, right? From the left side, like here's the number that we want to get to. And then every time n gets bigger, we're getting closer and closer and closer and closer and closer. And eventually we get so close that those numbers are basically the same. Okay, so now if we plug in 3, we're going to get 1 plus 1 over 3 now to the third power. Okay, so then when we do that, we have 1 divided by 3. Okay, we add 1, and then we take this to the third power. All right, so notice now we've gotten a little bit closer, right? Just by increasing the value of n, now we're up to 2.37, okay? So in terms of accuracy, we're much closer to the value of E now than we were when n was 1, okay? So now let's see what we get when n is 5, all right? So now 1 plus 1 over 5 to the 5th power. So 1 divided by 5 plus 1. Now take this to the 5th power. Okay, and so now we're at 2.48. Okay, or we can round it up. We can call it maybe 2.49. Okay, so n, the size of n went up. Now we've gotten closer to 2.71. All right. Next value, now we're going to jump. We're going to use 10. Okay, so 1 plus 1 over 10 to the 10th power. Okay. And so 1 divided by 10 plus 1 to the 10th power. Okay. And once again, we're a little bit closer now. We're at 2.59. All right. So we can say this is 2.59. Okay. So just by putting a 1 as our end value all the way to 10, right? We've gotten closer, but we're still really in terms of numbers, we're still way too far away to say that this is an accurate approximation of the letter E, right? Imagine you tell somebody pi is 3.14, and then someone's like, oh, you know what? Like pi is pretty much 3. Like that's way off, right? That's way off if you were calculating the area. Let's say you're calculating the area of a circle, and you decide to plug in 3 for pi. You're not going to be close at all, right? You're going to be off. So saying that 10 is large enough is not good enough. We have to keep going. We have to make the end value really large. And so that's why eventually the table takes us all the way to 100,000. Okay. And even then you could then try like 1 million, 10 million, 1 billion, right? The larger the end value gets, the more precise it's going to be. Now, typically the calculators have, they can only round it so close, right? So eventually it's like, okay, it's so big already that at this point it doesn't really even matter. But we'll see what it looks like when we get to 100,000. Okay, so let's keep going. Let's approximate now when n is 100. So 1 plus 1 over 100 to the 100th power. So 1 divided by 100 plus 1 to the 100th power, okay? You see that? Now that is getting close, right? Now that we've gone up to 100, now we're at 2.7, right? So we're like, okay, it's getting there, 2.7. And I believe we can round it to we'll leave it at 2.70, okay? We're close, right? We're close. N is getting larger, we're converging, right? We're getting close to that point. All right, now let's try with 500. Let me actually write this in here. So 1 plus 1 over 500 now. And that's going to go to the 500th power. All right, cool. We've gotten to 2.71, right? Now we're getting there, right? 2.71. In this case, though, let me see. What do I want to round this to? 2.715, maybe 2.716 or so. Yeah, 2.716. Okay, now we try with 1,000. Oh, you know what? We'll keep it right here. Okay, so 1 over 1,000 plus 1. Now we take this to the 1,000th power, okay? And then now that got even a little bit closer, right? Remember it was 2.7155, now it's 2.7169. We're getting closer, okay? So I'm gonna start utilizing a few more decimals. 2.7169. Okay, because we're getting a little bit closer to our E value, all right? But we're still not quite at the 2.718, right? So now when we try 10,000, let's see if that gets us any closer. Okay, so 1 over 10,000 plus 1 to the 10,000th power. Okay, so you see that once we've gotten to a number as large as 10,000, we've gotten pretty close to what the E value is approximately equal to, 2.71814, right? Now that's not quite the 2.71828, but it's getting pretty close. So we can say now 2.71814. Okay, and now finally we'll get to 100,000 and then we'll stop there. Obviously, the larger the number it gets, the closer we'll get. But I believe we should get pretty close to the 2.71828. All right, so the last one here. 1 plus 1 over 100,000 to the 100,000th power. All right, so 2.718, 2, and then it's 268. So pretty close, 2.7, 268. All right, and so if we continue to do this, eventually we would get to a point where, right, let me just show you, like, what if we tried like 10 million? I'm just gonna do it here on the calculator, but not by hand. If we took, let's say, 10 million, okay, plus 1 to the 10th million power, right? I've basically gotten about as close to that number as I can, right, where the decimals still matter, right? Once you get to like more than like 6 decimal places, like it really doesn't matter too much. It is not going to be a huge difference, right? So the approximate value is 2.71828. When I utilize 10 million, it's 2.71828, right? And then the only thing that's going to adjust is the numbers, the decimals that are after that final 8. Okay, so those, they're so small and kind of like insignificant. But the larger you go, the closer and closer you'll get. All right. But just like pi, where 3.14 is typically good enough for an approximation, in this case for us, we're only going to use a couple of values right after. So I'm going to be a little bit more precise, we're going to use 2.718. Okay, we're only going to use 3 decimals after, 3 decimal places after the decimal. All right, but that's essentially how we get to the value of E. Okay, now I know it's a little new, it's definitely new. If one of you guys ever took pre-calc, you may have seen some basic limits, but limits they're a huge thing in calculus. So basically, you're just trying to find like how close can I get to this value. The larger the number that you input, right? So this is telling you right here when it says that the limit as n goes to infinity, that just means keep plugging numbers that are getting larger and larger and larger. As you're approaching the larger numbers, you're going to start to close in on that value that you're trying to reach, okay? And so that's kind of the cool thing about limits, in that it allows you to approach something if you never knew where you were going to from the start. All right, so notice how the number, even though you're plugging in really big numbers, the number's not getting bigger, right? It is, but very slightly, right? It went from 2 to 2.718, right? It didn't go from like 2 to 2 million, right? It's just narrowing in on what the size of the number should actually be, okay? Are there any questions about this entire process?
No.
You okay? It's a little nervous for me because I haven't I have never taught a limit before, so so that's just like an introduction. Okay, so if you ever take a calculus later on in college, you'll definitely see this. You'll definitely see limits, and they show up like this. Okay, um, but don't worry, they're not too bad. All right, so now we can say from here on out, we're gonna utilize E for us is gonna equal 2.718. Okay, as the approximation that we're going to use. Okay, if we have to hand calculate it, but typically sometimes these calculators utilize the value E in here somewhere. You see it in my calculator, it's right next to pi. So if I were to close this out and I just hit E, right, it already has that kind of like number generated for me, 2.71828, right? And that's typically good enough. The same way that if I were to just hit pi, I get 3.14159 and so on. All right, so your calculator or any calculator, including Desmos, already has that built in. So sometimes you won't even need to type it in manually, right? You can just hit E, all right? Okay, so now let's move on. Let me go ahead and give a screenshot of the next problem, and so I can bring it in here. Okay, so now for part 3, it's a little bit of a challenging question. I think what I want you to get out of this is that remember that there's a connection between E and compound interest, right? So we spent this large amount of time kind of figuring out where E comes from, but eventually we want to use E to solve compound interest problems. So we're not gonna like spend all this time like figuring out like, you know, like the origins of E. We're gonna shift directly back into compound interest, right? Because those are the types of problems we're trying to solve. So for number 3, let me grab a screenshot of this real quick. And let's go ahead and we're gonna plot it here. All right. So it's kind of recapping what we just did, right? Saying that for increasingly large values of n, right, as n gets bigger, n then starts to approximate E, right? And E we know is approximately 2.718. Okay, so then it says to use a relationship between the expression and E, okay, to see how E can become part of a compound interest formula. Okay, so ultimately here it's asking us to like explain how each step got to the next step and yada yada. Honestly, I think it's a little bit too much. It's a bit of a stretch to get us to kind of like look at this. The big picture here is if I wanted to take a value, right, and I want you to like take a look at step number 4 in particular, this should be familiar, right? That's where compound interest, that's how a compound interest formula is built already, right? If we go back to our notes from investigation 3 when we first started, I have it saved here. Before we got to the really complex formula, which had the recurring deposit, we had compound interest formula, and take a look at that, right? 1 plus r over n to the n times t power, right? That was the compounding factor, because everything else, the a value in this case, represented just the initial amount of money that you put into the account. Everything else, right here, we'll call that the compounding factor, right, of the formula. So now if we go back, right, that's the same thing, right? That's the compounding factor right there, right? And look at what that compounding factor is equal to. It's equal to now what we're going to be able to replace with, but utilizing E, okay? But again, this is only possible to make the switch when you go from compounding at a fixed amount of times in a year. So for example, compounded monthly or yearly or semi-annually or quarterly, right? When you know exactly what the N is that you can plug in, you utilize what's in blue. That is the traditional compound formula. When you are given some piece of information that tells you now that you're compounding continuously, nonstop, at every single moment of every single day, then you shift over to the next side of the formula, which is the E. All right. So E is going to take care of all of the underlying math that's taking place when things are happening at a continuous rate. So it actually makes the formula much simpler because we know that E is just a number. It's not a variable. E is something that you could plug in for 2.718. And then you only have to worry about what's the rate and what's the time, right? Those are the two other variables you would have to be concerned with because now N, you don't have to worry about it because we're assuming that things are happening continuously, okay? So let's see, for part B, complete the following sentence in a way that explains the relationship. Okay. The value of an investment that starts at A and paid at an annual percentage rate of R and is compounded at shorter and shorter periods can be approximated by, and in this case, what we're saying, sorry, I got a helicopter again. All right, busy morning, apparently. All right. What is it that they're trying to get us to say here? So the idea is if we had a value of an investment or a debt, let's say we call that A, All right, so that's like, let's say that's the initial amount that you're paying in. Okay, it's paid at an annual rate, right? So we have R. It's compounded at shorter and shorter periods, right? So imagine, right, we're going from months to weeks to days to hours to minutes to seconds to half a second to quarter seconds, right? It's the amount of time in which it's happening at is getting smaller and smaller. Then at that point, we are at a compounded continuous rate. So that means that now we're going to utilize E as part of the formula. So now the formula that we're going to use is going to be approximated by, it's always going to start with your initial amount as an investment. That doesn't change, right? So now we're going back to A in terms of like, that's your initial investment. What is it that you multiply it by? Well, typically it would have been this had you been in traditional compounding stages, right? It would have been. But now that we have decided that it's going to get compounded at shorter and shorter periods, now we're making the switch over to utilizing E instead. Okay, so instead of using the left, now we use the right. So our formula now has been simplified because now what we're saying is it's the initial amount times E to the R times T. Let me write that a little bit clearer. Okay, so the formula here that we get to use from now on, okay, is going to be represented by final value is going to equal your initial amount of investment times E to the R times T power, okay? And that's essentially all that number 3 was trying to get us to do. It was trying to get us to kind of build our own final value formula when we are in compounded continuously. Okay, so this only works when it's compounded continuously. Just like before, when we would have to read carefully if it was simple interest or compound interest, now we have to read carefully if it's compounded at a monthly rate or compounded continuously, right? If it's continuously, then you know you're going to utilize the formula that involves E. Okay, if it would have said it's compounded, let's say monthly, then that means that you're only going to do it 12 times a year. Notice how there's nowhere to put the N in this formula, right? So how could you possibly do it? You would have to go back and utilize the formula that actually has N built into it, okay? Because the new one is making the assumption that you're doing things continuously, so there's no need to substitute an N value, all right? We already did the substitution for N values when we did this giant chart, right? So it's assuming that it's happening so many times that we have rounded that value now to 2.718, okay? So there's no need to do it again, all right? So here's what we're gonna use moving forward. As our future value formula, okay? Are there any questions so far? We got a message on the chat. Let's see. Oh, I can't see it. No. Okay, cool. Okay, all right, so real quick, I just want to go ahead and put this into use before we go. I want to give you an idea of like why did we go through the trouble of doing all this? Like, how do I even use it? All right, so number 2 and number 3 were just kind of introductions to get us familiar with what E is, right? You don't want to introduce some variable into or some constant into a problem without even understanding where it comes from. So now that we know where E comes from, we know how E can be used to find final values with a compound interest formula, right? It has its own special formula. Now let's see if we can actually generate some solutions from this. Okay, so let me just screen grab number 4 real quick. Okay. All right, so formula here, suppose the future value after t years of $500 compounded continuously is given by this function, right? So we have a $500 amount that was initially deposited, right? So because it was initially deposited as a $500 amount, right? That's our A value right there that shows up as the constant for this function, okay? Notice here that typically the compound interest formula just in general is F equal to A times E to the R times T, right? What do you notice? That instead of R, we have a value there already, right? That's the rate, right? We're being given the rate. We just have to know where to look for it. So that means that the rate, if it's 0.02, then really what that means is just it's a 2% rate, okay? So we're compounding continuously at 2%. All right, so when it's asking for part A, what is the continuous percent growth rate? Well, we just found it, okay? So what we were looking for is right next to the time, the product of whatever that decimal is, that's the growth rate, okay? So here we can say that the rate, growth rate, or I guess APR, is 0.02 or 2%, right? So that's for part A, okay? You just gotta know where to look. So the rate will show up as the product with whatever the time is. All right. Okay, now B is asking what's the APY? All right, well, APY is slightly different from APR. Okay, the rate that you're being told that it's going to grow at doesn't necessarily reflect all the time what you do end up with at the end of the year. Okay, so what is the APY? All right, well, one of the ways that we could do that potentially is maybe we can just plug in, maybe we could plug in 1, right? Because it's APY is annual percentage yield. So maybe just after 1 year, we can see what we get, and then we can find the rate based off of that. All right, so what if we did try plugging in T as 1? Okay, well, then we could get 500 times E to the 0.02 times 1, right? Only 1 year has passed. So it's basically the same thing as saying 500 E to the 0.02. Okay, so here's where we get to utilize some of this. We're going to use E. I have it already in my calculator built in. Let's do it through Desmos because we can all access that at least. All right, so if I type in E into Desmos, right, it automatically generates that for me, right? It gives me the approximation for the E value. So we want to take this E value to the 0.02, okay? So notice that it's generating that for us, and then obviously we want the 500. So go ahead and type in 500 in the front, okay? And there you can see that that is going to be the final amount at the end of 1 year, right? This is if you were compounding continuously at a 2% rate with an initial investment of $500. At the end of the 1 year, you're going to end up with $510.10, okay? So let's go ahead and see. All right. Okay, so then from there, that means that what was our gain? That was our gain here was, well, if you went from 500 to 510, then really you only earned $10.10, okay? And what was the percentage that you yielded, right? Well, it's $10.10 out of whatever initial amount you started with. Okay, so let's see what the true value of your yield was. So in this case, it's 10.10 divided by 500. Okay, notice how the yield is a little bit bigger than the interest rate, right? Your interest rate, your APR was 0.02. You actually yielded 0.0202, slightly a little bit more, okay? So then the APY, okay? Let me actually kind of rewrite this so that we can see the process. So up here at the top, you have the ending amount, right? 510.10. You subtracted 500 from that. Okay, that's how you got 10.10. Okay, that's how much you gained in that 1 year. Okay, now the gain only matters in comparison to where you started. So because you started with 500, then this is what represents your yield, right? What you truly earned by the end of the year, which ended up being 0.0202, right? So if you were to convert that to a percentage, then you're looking at 2.02%, right? A little bit larger than what the interest rate said that you were going to get. Okay, that's typically what happens. A yield, an annual yield, is usually larger than the APR, because this is the true value of what you earned. This was more like a prediction. Okay. All right. Okay, so I know I'm a little bit over time. I'm gonna go ahead and stop it here. I don't want to rush through part C and part D because they require a little bit of work, and a little bit of logarithm. So I want to go ahead and take a little bit more time on that on Thursday. But for now, I think we're in a good spot. We've at least gotten to the formula. We know where to find the rate. We can calculate a yield. And then from there, we're going to be able to utilize the formula in a little bit different ways to then find things like what is my balance after 2 years, or how long is it going to take to double. Okay. So I'm going to go ahead and stop here, guys. I hope everything so far is making some sense. I know it's kind of like choppy waters because it's a lot of it could be really new for some of you. Okay, but are there any questions for anything moving forward?
No, okay.
You cool? You good? All right, guys. Okay then. So I'll see you guys on Thursday. Just remember to keep working on some Alex. Stay on top of that.